Hey guys, so welcome back to your next class of Catalyst Concepts. Uh, so today we are going to look at something related to the resistance of an object, right? We already looked at what is an electric shock and we already studied about what is the meaning of resistance. We looked at the different resistances that the human body can have and why we need to be very careful when we handle electricity. Okay, so the question we are going to try to answer today is that does everything have the same amount of resistance? Like say, as we know, metals can conduct, and we also know there are so many different types of metals. There's also some other materials that can conduct. So, do all of them have the same kind of resistance, or does it differ? If I use steel, is it different than if I use copper, right? So, which one's better? Which one's worse? And what exactly is going to affect the electricity? Is what we're going to try to look at today. Okay, so um, for every example, we're going to try to take a very simple, let's say, comparison. Okay, so I'd like you to think about something like this. Say that there's like a big corridor, okay, like a space, and say that there are a lot of students over here. Okay, just a lot of them, not just one or two. Many students is standing here, and all of them are trying to get through this corridor. Okay, through this space, and there's like a lot of them. All the students going through this space is kind of, think of it as electrons trying to move inside of a conductor. Okay, we'll try to think of that sort of comparison and try to see if we can make some connection or no. Okay, so uh, let's talk about the first thing, and that is temperature. Okay, temperature. Does the temperature affect the resistance in any way? Does it increase or decrease the resistance? And if it does, how does it affect it? Okay. So electrons to move, whenever they move, they have some sort of kinetic energy, right? We already know that. So what happens if we change the temperature of an object? Okay. If we increase the temperature, then the electrons are going to accept more heat energy, correct? Okay, so with an increase in temperature, I can say that the kinetic energy increases with temperature. Okay, now assume that all of the students are walking through this corridor. Okay, you'll have a little bit of congestion, you'll move a little bit slowly, and somehow you will get. Now imagine that all of the students are trying to run through the corridor. Right, that's the difference between low heat and high temperature. When there's more temperature, there's more energy, and they try to kind of like run. So as electrons try to run or just move faster through the conductor, they'll start crashing into each other. Okay, now you can assume kind of like that this corridor is not completely empty. Say that there's like maybe chairs or like some boxes, whatever in middle. If you try to keep running in this corridor, you're gonna either hit the wall, or you're gonna hit the chairs, or you're going to hit each other, right? That means every time you hit, you're going to slow down, and that slowing down means you're going to reach till the ending late, right? So I can say that if your temperature increases, your resistance will also increases. Okay, resistance increases with temperature. Because of this very reason, the collisions will increase if the temperature is higher. And if the collisions increase, it means the speed is going to get slowed down and it will take more time to reach the same destination. Okay. So this is the first way that we are talking about. Resistance and temperature are directly related. More the temperature, more is the resistance. Let's talk about something else. Okay, let's talk about length. Let's talk about the length of the conductor. So say that again we have the same student example, but this time say it's a very short corridor. Okay, say you're in a room here. Okay, say this is that big room full of students reaching this room, whatever it is. Okay, two examples. of the students being in a room wanting to go through here, but the corridor length is very short, okay, just very small gap. And another example where the corridor is long, okay, it's a very long corridor. Same thickness, okay, same width, there is no change in the width, but just longer. Okay, you need to go more distance to reach the other room. Okay, now tell me in which case do you think the students will be able to reach the other end quicker, right? Because obviously this space is less, so there will be some sort of slowing down once the students try to go through here. Okay, say all of you are walking through here. Since it's congested, it will take you some time, but ultimately you will reach here. Okay, but if you try to move through the same space, but just longer, it's going to take you more time, right? It's quite evident. It's going to take you a little more time since there is the gap that you have is smaller, but it's also longer. Okay, so this means that as the length increases, the time taking you to get out of that tight gap is also increasing. So I can say that if the length increases, the resistance also increases. So I will say resistance increases with length. Okay, so this means to say if I have a very short wire, okay, it will have less resistance compared to the same size of wire but longer. Okay, same thickness wire but longer. If I have a short wire, long wire, I'll prefer a shorter wire because less resistance. If I have a longer wire, it will just take more resistance. Okay. That's the point I'm trying to make. So this we can write like this: R directly proportional to L, where L is nothing but length of the conductor and R is nothing but the resistance of that conductor. Okay, so we are done with two conditions. Let's look at the third one: area. Okay, area. By area, I mean cross section area, basically thickness of the conductor. Like we spoke of wire, right? If you cut it, it kind of looks like a tube, right? So again, we can try to take the same example. Let's say that you have again the same two rooms. Okay. Like this. So over here, the difference being in your second case, your room or your let's say your corridor is much bigger or wider. Okay, this is a very thin corridor and that is a very wide corridor. So you see the difference, right? Now again, students have to move from this end to that end. In which one will they reach faster? Through the thin way or through the wider way? Okay, more specifically narrow and wider. Okay, this is less and this is more wide. And obviously they're going to be able to go here faster, right? Because there's more space for the students to go through, for multiple students to move through, and they'll reach faster in this case and this case. Okay, so over here, resistance decreases when area increases. Okay, so they are inversely proportional, what we say. Okay, if the area increase, the resistance will decrease simply because there's more space for the electrons to flow. Okay, and by area I mean the area of the conductor. Okay, basically the thickness of the wire, how fat it is. All right, so since it is indirectly, we write it like this: R proportional to 1 by A, meaning as area increase, resistance decrease, or area decrease, resistance increase. Okay, that 1 by means inverse. All right, so these are three factors we have seen so far: temperature, area, and length. Finally, it will come to, we haven't talked about material yet. right? We spoke of copper, steel, which one is better, something like that. Okay, does it really matter if say that temperature, length and area, all of them are the same, right? Will the resistance be different for copper and for a different metal at the same time for the same amount of let's say area, length, temperature? Will the resistance change? So that is something called as specific resistance. Okay, so what we will do is, we know that R is proportional to L and to A. So I'll write it as R proportional to L by A. Okay, I just combined these two together to write this. From here I'll get something called R equals to, since I'm taking the proportional into a constant, equal, so I'll take a constant called rho. Okay, this is called rho. It kind of looks like a P. Okay, it's called RHO, rho. Okay, this rho is nothing but specific resistance of that one material. If I have to find that out, I just cross multiply it over here. Rho equals to R, A goes up there, into A divided by L. Okay, this is nothing but your specific resistance, and this specific resistance will change for every different material. Okay, we calculate the specific resistance at one specific temperature for every material, and for each material it will be much different. Okay, so if you look in your readers, there will be a small table that tells you about the specific resistance of each material. I think it's on page number 191. Okay, there will be a whole table which will tell you the name of the material and the specific resistance. And if you want a good conductor, you will take as something with the least amount of specific resistance. Okay. So that is the reason why we use copper in our wires, because copper has very low specific resistance. It means it will be a good conductor for us. Okay. So this is what four factors that we talk about: temperature, length, area, and the material itself. And when we talk about material, the specific resistance of that material. It's also called as resistivity. Okay, specific resistance, resistivity mean the same thing. Okay, so that's it for today. If you have any questions, doubts, comments, please drop them in the comments below, and I will see you again in the next class. Thank you.